welcome back to the linear algebra series. Today we're going to be talking about vector rotations. Now vector rotations are quite simple. It says if I take a little line here, say this guy, right, this line, and I want to rotate him some angle around a trace of a circle, how do I do that in linear algebra? Well, if you remember trigonometry, it's going to require some trigonometry. So let's get into it. And first I wanted to quickly review polar coordinates. If you remember, polar coordinates seeks to go from some value x, y to a length r rotating around a theta. Okay, so it's a function. It's a function of theta as a function of r, if that makes sense. So the best way to show this is if I have some vector, right? And let's say I'm at the point xy. Like this. Well, I know to get there I traveled some value x and I traveled some value y to get there. But we simply simplify it and make it a straight line to that point, which in this case we're going to call r. And to make it a two-variable function, we add a theta. And what this does is it sweeps around the unit circle, right? So here's that r. It's going to sweep like a clock around by some amount of theta, okay? So it's quite simple, polar coordinates, but the best thing to pull out of this is the relationships. Now, if you remember from your calculus days, or if you haven't had calculus, you may or may not have done this. How we define x and y within the realm of polar coordinates is we say, well, if I look at cosine of theta, well, that's simply adjacent over hypotenuse, so that's x over r, which leads to the idea that x is equal to r cosine of theta. And similarly, we can do the same thing with sine. So we'll find that relationship, and then we'll get the identity that y is equal to r sine of theta. Okay, I shouldn't have to review trigonometry. Hopefully you can rationalize this. But the idea is that we can express rectangular coordinates as polar coordinates, and that's useful if you're going if your point is moving around a circle. It can be quite simplifying in those ways. Okay, so now that we have just a quick review of polar coordinates, let's talk about vector rotations and how it applies. So let's make a little definition here. Imagine I have an xy plane and I have two vectors on it. This is vector v, and let's call this vector here, let's call this, that's not quite a circle, it would be like here-ish. Let's call this vector w. Okay, what I want to do is have a way to define w. How can I define w as v? And if you remember from just the more simpler standard matrices and those transformations, we know that we just need to scale it with some TA, which the TA is the standard matrix. Okay, so w can be thought of as v times some TA, which is the standard matrix. And this will only work, of course, if you're going in a circle, but usually you're not working with that logic. You're working with the logic that, okay, I want this vector v to rotate this amount of degrees. Okay, pretty simple. We know that the vector v has two components. It has an x component and it has a y component. But the same could be said for w. W also has some components here. He has a y, which we're going to call y prime. And it also has an x component, which is x prime. Okay, so hopefully you can follow that. We're just making some ideas here. Now let's define some angles here. I'm going to redraw the vectors because it is getting really messy here. Give me 1 second. This is critically important for understanding here, because you have to do it this way. You can do it one of two ways. You can define the angles one of two ways. You need to do it this way for the proof to really hold any substance to it. So this angle here we're going to call theta, and we're going to call this angle phi. Okay, so very important. Don't do this whole angle, because that will trip you up. It's just going to give you you're going to get stuck in the proof, basically, which is no fun. Okay, so now that we have that, let's define some things. We know that the vector w needs to be expressed as v, so what I want to do is express y prime as some junk of this normal x stuff, and x prime as some junk of this stuff here. Right, so that's the goal. Let's do it. Well, let's start off with the most simple definitions. How can we define x and y? Well, if we know that cosine of theta, or sorry, I should say our cosine of theta is equal to x, whereas our sine theta, in our case, is equal to y. All right. So we know this to be true. These are fundamentally true. All right. But what about x prime and y prime? Well, notice they're a little different. We're not just taking the angle phi between them. We're taking phi plus theta. Now this is the critical part here. When we want to describe x prime, same kind of logic. It's still our cosine, but this time it changes. It's not just theta anymore. It's theta plus phi, right? It swept out an angle of phi. And with y prime, again, very similarly, our sine of theta plus phi. All right? So we know this to be true as well. But if you remember from your beautiful algebra days, and I always, or probably learned this in geometry or trig, one of the two. I learned it in trig. We can rewrite these, okay? It's the double angle identity, I think. I think that's what it is. Please don't quote me on that. I probably have that wrong. I always forget the names of them. Well, we know that cosine of theta plus phi can be rewritten as cosine of theta. Remember, these guys go together. Cosine of theta, cosine of phi. And then it's going to be minus sine of theta, sine of phi. And if you're curious what I mean by phi, maybe you haven't seen it, it's this symbol here. This guy. Phi is kind of not used. It's used in Calc 3, but you may not have seen it if you've only taken maybe Calc 2 or no calculus at all. Just wanted to point that out. Sine of theta plus phi. Well, what's this identity? This is going to be cosine of theta, sine of phi, plus sine of theta. And what's the only guy left? Cosine of phi. All right. Well, why did we do this? Well, it's to expand this guy. And let's do that. Let's just add some r's where we need to. I won't write it all out again, but here we'll get an r. If this is r cosine of theta plus phi, this is r sine of theta plus phi. Well, we just get r's in front of everything. like this. So sorry, it's a little messy, but every little white spot's a little r variable, the length of that vector. But do you notice anything? I really hope you do, because this is the cool part. Well, what's this? What's this? What's this? And this. And this. And this. This is like so cool, guys. Whenever I see something really beautiful in math, just like beautiful simplifications like this, it's better than like ASMR. It's better than sex. X prime, y prime, right? This is x prime right here. I hope you can see that, right? Because that's what we defined up here. Y prime, I again hope that you can see that, because right here, what's our cosine of theta? That's x, and x, and y, and y. Isn't this so cool, guys? Oh my goodness gracious. So x prime is really just x times cosine of phi minus y sine of phi and this is x sine of phi, and this is plus y cosine of phi. Now this is cool, guys. This is amazing. Let's pull out some variables in the linear algebra fashion. So let's define this to be x prime, y prime. This is now a vector. And let's pull out the x's and y's here. This is cosine of phi, negative sine of phi, sine of phi, cosine of phi. And that's going to be, we're pulling out the multiple vector xy. Okay? That's exactly what we tried to do here. We found this, basically. So this is vector w. W equals, and the TA in this case, and I'll mark my things here actually, I think that'd be better. This is our W in the case up front. This is V, and this is TA right here. All right. So what you do in the case of rotations of a vector is, let's say you have some vector here. Let's say 1, 2. And you want to rotate it some degree phi. And remember, this is critical because sometimes you might get tripped up with the angles. It's not theta plus phi that you're looking at, right? Because you might look, okay, you want to move it 20 degrees such that it's 40 degrees from the x-axis. So it started at 20, you move it an extra 20. You need your phi. Typically you'll see this as theta. It needs to be the 40 degrees, or sorry, the 20 degrees, not 40, the sum. You don't want it to be the sum. You just want this component here, right? Because that's how we defined it to be, right? And hopefully I've shown that with the distinction between theta and phi. And what you do, again, is you just plug in some phi, and you get this nice TA scale version of v, and you get out w, and that's going to rotate your vector around